The world isn't perfect. Voltages are never precise. Power surges happen. Components fail. One of the main jobs of an engineer is to anticipate those faults and to predict how the system will behave when confronted with a fault, or a combination of faults. With that information, the engineer can determine the best way to respond when faced with out-of-spec voltages, surges, or failed components. Hey, that engineer had better be diligent. The consequences of failing at this task can be dire. If your product doesn't handle power surges well, it will likely exhibit an increased field failure rate, and there goes your reputation in the market. Hey, maybe lives depend on the proper behavior of your system, and failure, that's just not an option. Maybe there are safety concerns, uptime concerns, or maybe just a need to keep everything moving at a steady rate. In any case, you do not want to be this guy. The right time to think about system faults is before they happen. Today, we're going to think about faults that can happen when providing power in electronic systems, and specifically, we're going to look at 3 kinds of system faults. Voltage faults happen when the supply voltage exceeds the voltage rating for a device, or dips below the minimum specified voltage for some period of time. It might be due to a voltage surge, ringing due to a sudden change in the load, or even a voltage reversal. Current faults happen when excessive current is drawn by a device. Now, a current fault doesn't always mean that something has failed. It may just mean that an excessive current was drawn during the startup sequence for a device. But it may be due to a failure, such as a short circuit, or current flowing back into the supply due to a surge at the load end. And finally, there are thermal faults. Now, these are faults caused when the temperature of a device, whether caused by internal heating of some component or the temperature in the environment, exceeds the rated operating temperature. Voltage, current, and temperature go too far outside the given boundaries for any of these, and you're in trouble. Let's have a closer look at each of these. Now, voltage faults can happen for several reasons. A common reason is hot plugging of a board into a powered rack or chassis. Now, think about what happens there. The board contacts connect to the backplane, and current suddenly rushes in to charge capacitors that have been discharged for weeks. Now, maybe the backplane can't supply that current, in which case the voltage dips. But when the voltage recovers, it doesn't just return to the nominal level. Inductance in the backplane and the wiring ensure that the voltage will likely overshoot and ring. Now, as an engineer, you have to plan for this. Hope is not an option. And it's not just hot plugging. A blown fuse in one board can cause a voltage spike in the other boards. And environmental concerns, a near lightning strike or fluorescent lighting can cause surges as well. Let's take a look at a couple of kinds of voltage faults and see how we can manage their effects. Electrical fast transient, or EFT, is a common kind of voltage fault. Now, the key word here is fast. An EFT event has a rise time of just 5 nanoseconds, and the whole event lasts a little more than 50 nanoseconds. But the amplitude of the pulse can be impressive, from 500 volts to 4 kilovolts. Protecting against EFT requires a fast transient voltage suppression diode like the SMAJ series. Now, these diodes typically switch in less than 1 picosecond, but be aware, for a 24-volt system, it's not unusual to use a transient suppression diode with a nominal reverse standoff of 33 volts. But when this diode is carrying its peak pulse current of 7.5 amps, the clamping voltage may be as high as 53.3 volts. And that's the voltage your protection system has to expect, even if it is just for a few nanoseconds. Ringing happens when a switched load is situated far from the power source. Now, in this case, the combination of wire and closely spaced conductors behave like a poorly tuned tank circuit, and when the load is suddenly switched on or off, the system will ring just like any parallel LC circuit. Now, in this test arrangement, we applied a brief short circuit at the end of the cable. What we observed was a ringing that peaked at over 50 volts, more than double the input voltage. And the ringing forced the voltage down to just 11 volts. As you can see, depending on the 24-volt supply to be nice and steady, that's probably just wishful thinking. And just in case you thought that was an exceptional case, take a look at this. Here, the power supply for the programmable logic controller is at one end of a long bus with hot pluggable modules all the way down. And that power supply isn't particularly precise. It may vary from 19.2 volts all the way up to 30 volts. And the ringing on the bus when modules are inserted or removed may push towards 60 volts. Now here's what you need to remember. If you're designing for any of these environments, you'll need to make sure that your equipment can tolerate peaks and surges far in excess of your rated input voltage. But voltage is not the only destructive influence. Excessive current flow in a circuit can cause damage as well. Sometimes the excessive current can be due to something the designer overlooked, like inrush current as capacitors charge on power-up. Sometimes a careless worker might drop a metal tool into energized equipment, causing a short. Hey, sometimes a component just fails. Well, regardless of the cause, the results can range from inconvenient to catastrophic. Inconvenient if you need to replace the failed module with a spare, and catastrophic if the failure results in a fire. It's in everyone's best interest to deal with current faults before they happen. Inrush current is something to which particular attention should be paid. When you connect a capacitor to a power supply without any circuit protection, the rate of voltage change with respect to time is instantaneous, and the dV/dt is infinite. That means that the instantaneous current can be practically infinite as well, governed only by the equivalent series resistance of the capacitor. And since modern capacitors have very low ESR, there just isn't much to natively limit that inrush current. Say hello to burned traces, say goodbye to functioning hardware. And, of course, if by some chance the system voltage is reversed, you're likely to see a lot of burned traces as the system tries to handle the reverse current. The third bad guy on our most wanted list is thermal faults. The causes are many. Maybe it's just a dirty filter that's blocking ventilation. Maybe it's just a hot Texas day. Or perhaps one or more fans are failing. Hey, mechanical parts do fail, you know. Whatever the reason, keeping track of the internal temperature of your equipment is essential. Overvoltage, undervoltage, overcurrent, temperature extremes. Think about them, prevent them where you can, manage the ones that can't be prevented, and have a plan. Or somewhere along the line, you're likely to have a very bad day, but how to manage the unexpected? Well, in the past, the solution has been to use discrete components to manage the worst offenders. A transient voltage suppressor for fast transients, a metal oxide varistor for slower transients, fuses for overcurrent, and all kinds of voltage, current, and temperature monitors. Hey, sometimes an IC can help, but it doesn't solve the larger problem, and here's why. First, are you absolutely certain that your solution is robust enough to do the job when trouble comes? Has it been thoroughly tested? Are you sure? The issue here is that circuits that may kick in only a few times over the life of the equipment and only in the harshest of circumstances are notoriously hard to test, and the performance of the protection circuitry is tough to verify. Now, second, with design trends dictating smaller form factors and increased functionality, there's a lot less room for anything that doesn't directly contribute to the designed functions. So, are you really going to dedicate a few dozen components in an already cramped space to protection that will be active only a few times over the life of the device? Really? Well, finally, you have to think about the total cost of the solution. That fuse that you put into the equipment to protect from overcurrent, well, what happens when it blows? You have to send a technician to replace the component, or the board, or the entire device. And even if you designed a system that failed more gracefully than a fuse, you might still need an on-site technician to bring the system back up. Now, ideally, the protection system should be robust, easy on the system designer, and should easily pass qualification tests. It should be highly integrated to minimize space and enhance reliability. And the solution should have a good fault management story that doesn't involve rolling a truck every time there's a fault condition. Okay then, let's design the circuit protection device we really want. Well, first, we want to integrate as much as we can, including the current carrying elements, and that usually means power MOSFETs. And as long as those switches are in there, let's integrate current sensing as well. The circuit should be able to detect and limit both forward and reverse current, and we should have programmable limits for the current, as well as under and over voltage. And when a fault is detected, we ought to be able to determine what should happen. Just a notification, system limits, or full system shutdown. And if we do shut down the system, should we try to restart or just stay turned off? And finally, we want to be able to sense and respond to temperature extremes, and that may include folding back the current when the temperature begins to approach a limit, or it may involve limiting the power supplied to the attached devices. Well, you're probably not surprised that Maxim has thought a lot about these problems. The solution we've created is the Olympus series of power protection devices. They're small, they can significantly reduce the space you have to devote to circuit protection, and they can make qualification much easier. Here's how. Let's start with the MAX 17608 family of circuit protectors. First, notice that this is a wide voltage range part. It can manage voltages as low as 4.5 volts or as high as 60 volts. Inside, you get settable under and over voltage sensing, an internal current sense element with limit values from 1/10 of an amp to 1 amp, and negative polarity protection all the way up to 60 volts. You can set the fault response mode, and fault outputs for both the current sense and voltage sense go to the system, as well as an analog indication of the load current. But what about size? All this functionality comes in a 3mm square package. All you add is a few resistors and some low-value filter caps, and you're ready to go. Need more power? Well, consider the MAX 17526. You still get internal current sense, an internal FET switch, and internal under and over voltage protection, but this device handles up to 6 amps. Just add an external in-channel FET for reverse voltage and current protection, or bypass it if you don't need the reverse protection, and you also get adjustable power limits. Now, let's take a peek inside the MAX 17526 and see how it does all this stuff. Now, one thing to recognize is that this part includes a MOSFET switch right on the die that's controlled by logic inside the device. If you understand the logic that turns the FET on and off, you'll go a long way toward understanding the operation of the device itself. When you first apply power to the circuit, the FET is held off until the input voltage crosses the under voltage threshold. And when this happens, the FET is turned on and the flag output is cleared, and the system receives power. As long as the input voltage is between the under voltage and over voltage thresholds, the system remains powered. But as soon as either threshold is crossed, the internal FET removes power from the system, and the flag output becomes active. Now, in this way, the system is protected from excessive voltage, insufficient voltage, and reverse voltage if the external FET is used. Now let's talk about reverse voltage for a moment. This happens when a fault causes the output voltage to be shorted to a higher voltage rail. That's bad news for the system that's directly seeing the high voltage event. but the system protector has to minimize the damage to the rest of the system, to anything that might be getting its power from VSys. The worst that could happen is that the overvoltage could be communicated to the VSys circuit, and the resulting overvoltage might result in a lot of damaged equipment. But with reverse voltage protection, the extent of the damage is localized. As you see in the scope capture, even though Vout has suffered a fault, VSN has been protected. A slight ripple is all you see as the external FET switches out. Best of all, the reverse current is cut off within a few microseconds. The local system controller may or may not survive the fault, but the rest of the system is protected. Another common problem is overcurrent due to startup inrush. Now, this happens because, very commonly, all the filter capacitors in a powered-off system are discharged. As soon as the supply is turned on, the initial surge of current goes to charge those capacitors, and as we mentioned before, modern capacitors have a very low equivalent series resistance. So if you just turn on the power and allow the capacitors to charge without any limitation on current, you may well find a lot of blown fuses. The MAX 17526 has a startup current limiter that keeps the inrush current at or below a given threshold, 1 amp, 1.5 amps, or 2 amps, depending on the version of the part you use. A short circuit can occur for a lot of reasons. Somebody drops a tool into the chassis, a device fails in a short, or someone miswires a load connection. A short is always a problem, but the right circuit protection determines whether it's a minor inconvenience or a difficult and expensive exercise. Now, in this scenario, something bad has happened on the load. The nominal 100 milliamp load is suddenly increasing at a rate of 10 amps per second. Something failed, and there's no time to diagnose what it is. The best thing is to get that short circuit off the system, and now. From the waveform, you can see what happens. Within a few tenths of a second, the circuit protector kicks in, turning off the output and reducing the current to 0. At the same time, the flag output goes active, alerting whoever's listening that there's a problem. Now that the immediate danger has passed, you can figure out what happened. You can fish the screwdriver out of the equipment, or you can inspect the circuit board to determine which component failed, or you can correct the wiring error. And once you've corrected the fault, you can restore power, and disaster has been averted. Now, you know you're in a reverse current situation when the Vout pin is at a higher potential than the VSN pin, but here's the thing. A minor reverse voltage isn't sufficient reason to call an emergency and shut down the system instantly. If the output is higher than the input by only a few millivolts, well, it's okay just to ramp down the protection FET relatively slowly, say over about 20 microseconds. It may be that the load is light and the input bus saw a minor voltage dip, and that's no problem. The power will be restored in a few microseconds, and the output capacitor will hold up the load during that time. But what if the difference is greater, say more than 100 millivolts? Well, in that case, we need to turn off that protection FET right now. We'll turn off the gate hard within about 100 nanoseconds to keep current from flowing back into the system bus and potentially damaging other modules. Now, of course, it's one thing to protect your system, but what protects the protector? Well, the MAX 17526 is perfectly capable of taking care of itself, thank you very much. For example, let's say the load is really pulling down the current. Now, The MOSFET in the MAX 17526 can handle the current, but it is going to begin dissipating some heat, and that heat will raise the die temperature, and if it gets too high, it could compromise safe operation. The MAX 17526 constantly monitors the die temperature, and if it sees the temperature approaching the limits of the safe operating area, it begins folding back the output current. Reducing the output current means less heat being dissipated, and that means reduced temperature. Once the current demand is reduced, the device returns to normal operation. Now you've seen how the MAX 17526 can limit inrush current to a prescribed maximum value that allows the input voltage to rise slowly and limit the current to the load. Well, the same principle can be applied to power. Power is the product of voltage and current, and it's power you generally have to worry about when you consider heating of external components. If you know that your load can only dissipate a given amount of power, you might consider applying a power limit factor. The MAX 17526 does that for you. It computes the product of the output voltage and the load current, and backs off the current if the power exceeds the established threshold. You can set a current limit and a power limit at the same time. In that case, if either current or power exceed their established thresholds, then the current will fold back, and the device will keep the load supply in check. Okay, so you've seen all the things this device can sense and how it responds. The most common response when confronted with a condition that requires the device to limit the current to the load is, well, to limit the current to the load. But what I haven't told you yet is that this is not the only possible response, and in fact, it might not be what you actually want the device to do. Actually, I can think of at least 3 ways I might want the system to respond to a fault. First, I might want the power protection circuit to act like a fuse or a circuit breaker. If my system is safety critical, I don't want to take any chances. Just turn off the power and wait for some kind of personal intervention before turning the power back on again. We call that latch-off mode, and you enable it by connecting the CL mode pin to ground through a 220k ohm resistor. But for most systems, just failing safely isn't the very best option. Utility companies use a circuit called a recloser to attempt to reconnect loads that have exhibited some kind of fault. If the fault was just a transient event, the recloser reestablishes the connection, and all is well. Now you can set up the MAX 17526 to do the same thing by just connecting the CL mode pin directly to ground. Now when the device senses a fault, it will turn off the output for about 720 milliseconds and then reconnect power to the load. If the fault persists, the circuit will continue trying to apply power, but since the current is always limited, the potential for damage to the circuitry and the load is reduced. Now finally, it may be okay to just keep providing power to the load at the current limit threshold. Of course, depending on the nature of the fault, that may mean that the voltage to the load is reduced, and it may mean that the current to the load will be further reduced because the MAX 17526 senses an overtemperature condition on its die. But if that's the behavior you want, then just leave the CL mode pin open. Hey, regardless of which fault response mode you select, the MAX 17526 will make sure that the load is protected and make sure that no load fault will affect other equipment on the power bus. Now, probably the most important user-settable value is the current limit. And the MAX 17526 makes it easy to set any current limit between 600 milliamps and 6 amps. Use this formula to compute the value of the resistor to use in the set-I circuit, and the current will automatically be limited to the desired value. Now, the set-I pin actually connects to an internal current mirror with a transfer ratio of 25,000. Now, to illustrate, if there is 1 amp flowing in the load circuit, the set-I pin would drive 40 microamps into the current sense circuit. So if you have a 10K resistor in the set-I circuit, that 40 microamp current would develop 400 millivolts across the resistor, and the internal circuitry in the MAX 17526 senses that to determine when a fault occurs. Now you can use that voltage to determine the load current. Just use an ADC channel in your supervisory microcontroller and perform the necessary scaling in software. And this way, the set-I pin really performs double duty. It's a way to set the output current limit, but it's also a way that you can monitor the load current. As you can see, the MAX 17526 addresses just about every concern we have for circuit protection. You'll still need to address very fast transients like EFT, but the MAX 17526 forms the core of a robust circuit protection scheme. Now you know why circuit protection isn't nearly as simple as it appears at first glance.
For more information on this topic, please go to our website at www.maximintegrated.com under Products, Power, Protection and Control. Thank you for watching this video, and see you again in another educational video of Maxim Integrated.